Let's get ready to do some math. Back with another distance learning lesson for pre-calculus owners. All right. So hopefully you tried your homework. I know the numbers are a little nasty. I always do the easy problem in class. No, just kidding. It's really all about this expansion right here. This is what I care about. So here you have to approximate the area. X cubed plus 1 from 0 to 1 looks a little something like that. So pretty simple. Looks a lot like what we had yesterday. Doesn't start at 0, so it makes it easier to see what's going on with squaring off. Right Riemann sum. Remember, you want to look at each rectangle, take the rightmost x value, plug it in to determine the height, draw a horizontal line. We can see this is an upper sum and over approximation. I did it here by getting each area separately. But remember, you don't need to do that. You just need to worry about first putting your delta x. How the heck do I get delta x? Well, it's b minus a over n. Okay, upper bound minus lower bound over the number of subintervals. Here it was equal to 1/4. I stayed fractions here. You can go 0.25 if you want to. It's the same thing. So start with that delta x right there. Then inside here, just think about, that first rectangle. Starts at the lower bound, ends 1 delta x later. Since it's a right Riemann sum, we plugged in the 1/4, and that means you put a 1/4 right here. And to go from one f of to another, just keep adding delta x. Okay, so just add 1/4 each time, which you can see that's what we did right here. Okay, and that's the expansion. Then put it in your calculator. It looks like I did all these and I kind of broke it down. You could do this stuff by hand as well. You could do it without a calculator. You're not really expected to, so try not to freak out so much. And you can see over approximation because it looked like an over approximation. Now we have that confirmation if you happen to do the exact area just for the heck of it, which is pretty easy to do. You could even use math 9 if you want to. So look, left Riemann sum, just start with delta x. Okay, but now you start with the left most x value, which is 0. Then just keep adding delta x's. And a midpoint Riemann sum looks annoying, but it's not really that bad. Here, if you want to know what each of these pieces are, you don't need to do this. But remember, if you want to get the number in between two numbers, you want to average those numbers together. If I were you, it's kind of an old answer key. I don't do it exactly like this anymore because it's so much simpler to just be like, all right, start with delta x. Then just worry about the first rectangle, which we know starts at 0 and ends 1 delta x later. And then to get the number in between, just average those two numbers. 0 plus 1/4 divided by 2, that's 1/8. And then once you get this 1/8, you could just keep adding 1/4 each time. That's adding delta x. Maybe instead of adding 1/4 for delta x, remember, delta x equals 1/4, but that really equals 2/8, right? So I would actually add 2/8 each time here, and you can see that's exactly what I'm doing. So these really aren't terrible problems, and these are kind of antiquated. They don't really ask you to do it like this anymore. And sometimes they do, and it could show up, and we'll talk about it next year in class. We use it to prove a bunch of other things as well. But these are more the types of problems you're going to see in the AP exam. Okay, so you got 6.2, this ditto right here. Number 1 is actually from the 1997 Advanced Placement exam. Who has 2 thumbs and took the AP exam in 1997? This guy. 1997, I'm like, that wasn't long ago. It's 23 years ago. Anyway. Wait, now you can figure out how old I am. We're not going to do this problem today. That's a homework problem right there. We're going to jump into number 2. Number 2. And you can see, let's read. A lot of people in math are like, well, I just look at a problem and know how to do it. That's not happening in AP Calculus. And this is even a very much truncated version of an AP problem. I can tell from the font. Let's read. Rocket A. Rocket A. What a name, right? I invented a rocket. It's amazing. I can't believe I've done this. What should we name it? Something very interesting. Rocket A. Rocket A has positive velocity after being launched upward, right? Something's moving upwards. Velocity is positive. We talked about physics. Remember that stuff? After being launched upward from initial height of 0 feet at time t equals 0 seconds. It's actually something known as initial condition. Something we'll talk about next year. The velocity of the rocket is recorded for selected values of t over the interval 0 to 80 seconds, as shown in the table above. So we don't have a function represented algebraically here, which you could easily turn into a graphical representation, as long as it's something that's not too difficult to deal with. Here we have a function represented numerically, or tably, if you want to say it that way. And that means we don't know what's going on. Okay, people are like, yeah, it's easy. Just graph it and draw, connect the dots. You don't know what's going on in between these t values right here, okay? You do know something. They tell you the rocket has a positive velocity. People are like, yeah, you can see the velocity is getting bigger. They have to stay positive, but they're not always necessarily getting bigger. I mean, this could go from a velocity of 5, maybe to a velocity of 4, then up to a velocity of 14. the rock is being launched upwards. That's not really going to happen. It's not going to head back downward and then head back up. But you just need to be careful when you're given a function represented numerically. Use a right Riemann sum with 3 subintervals of equal length to approximate this integral right here. What you can start to learn is that these Riemann sum expansions and the trapezoidal expansion we'll talk about next year, we talk about saying, saying that there are ways to approximate areas, but there are actually ways to approximate definite integrals. And integrals don't always represent areas. And I told you last topic, integrals can be negative. Areas can't be negative. Something we'll talk more about next year. But they want us to use a right Riemann sum and 3 subintervals of equal length. That's the important thing, okay? Because that means if the subintervals are of equal length, that means you can use an expansion. So here the integral from 10 to 70 of v of t with respect to t is approximately. Remember, we always start by putting delta x, only in this case it's not delta x, it's delta t, but that shouldn't bother you, okay? Delta t, still going to be b minus a over n. Now be careful, b is the upper bound, and a is the lower bound. On the integral, not on the table, don't be doing 80 minus 0 divided by 3. It's going to give you a weird delta t that you're not going to have values for. Anyway, you want to make it 70 minus 10 divided by 3. They do that a lot, too. They'll change the interval, the bounds on the integral, different from the table. They want to make sure you're paying attention out there. Pay attention. Wake up. And look how cool this is. For delta, delta x before was a 1/2. It was 1/4. It was, really small. This is 60 divided by 3. That's 20. And those are the delta t's and delta x's you typically actually see in the more real-world types of problems. So you put that right here. That's our delta t. Last time it was delta x. Then we started with an f of. In this case, it won't be an f of. It'll be a v of. It's the same type of thing. All you got to think about is that first rectangle, right? That first rectangle that starts at the lower bound and ends 1 delta t later. So ends at 30, right? Because if delta t is equal to 20, 10 to 30. Since it's a right Riemann sum, I don't plug in the 10 to determine the height because that's on the left. I plug in the 30 to determine the height. And then 3 subintervals means 3 rectangles. I need 3 heights. Here's 1 height. The next height, remember what we do, v of, just add delta t, just add 20 to get a 50, plus v of, just add another delta t, which gives us a 70, and that's it. That's the expansion right there, okay? As far as what you could do for work, v of 30, now let's get the value. We know it's what, 29? All right, plus v of 50, which we know is 40, plus v of 70, which happens to be my lucky number, which is 47, okay? And you can actually leave it like that if it's a part 2. If it's a part 1, you're obviously going to want to calculate what it is because it's going to be in multiple choice. Should be able to do it without a calculator, okay? 29 plus 40 gives me 69 there, plus 47. All right, 69 plus 47. Is that 116? Is that right? I feel like that's wrong. Is that correct? Who's checking my work out there? I'm so terrible with mental math. Let's check it with the calculator. No, I'm not checking with the calculator. I'm just writing it down over here. But when I write it down and try it again, for some reason, sometimes it sounds like I'm using the calculator. Yeah, I'm right about that. Okay, the 116. Okay, and then multiply it by 20. We'll get 2,320. We'll talk more about, next year, what this actually represents and what the units are. For now, this is fine. Really, it's about the expansion and calculating things in your head. I struggle with that more than anything else on any calculus problem. It's just mental math. It's the weakest part of my math game. Nothing wrong with having weaknesses in your game. Just keep working on it. That's the important thing. What does this actually mean? Well, we integrated velocity, right? If you integrate velocity, you should know what you get back. Velocity, that's somebody's derivative. That's somebody's derivative in there. Whose derivative is velocity? Position's derivative. So if velocity is in feet per second, we get back an answer that deals with feet because it's in position. What's actually really going on is velocity is the rate at which position changes, the rate of change of position. If you integrate the rate at which position changes, you actually get to get the change in position, okay? You're going to get back a position function, then you're going to plug in the 70, subtract the plugging in of 10. It's going to figure out where the plane is after 70 seconds. How far it's traveled, minus how far the plane traveled after 10 seconds. It's actually going to give you the change in the distance of the plane from 10 seconds to 70 seconds. It's actually going to give you, when you integrate the rate of change of position, you get the change in position. It's actually the displacement in the plane. Since it was always has a positive velocity, it was always moving in the same direction. That means that the plane has traveled this far from 10 seconds up to 70 seconds. Sorry about my brain blurb there. I think before I was talking about, hey, before, we don't know what the velocity is between 5 and 10. The velocity might dip down. I think I did this, like, to show the plane was going to, it's not the way it would work, right? The velocity is positive, plane would always be heading upward. It's just that at certain speeds, you know, here it looks like the speeds are getting greater, like it's speeding up the whole time. It's not necessarily what's happening. You know, maybe there's like a 4 in between here. So maybe it's going and it slows down a little bit and then it speeds up. So sorry, I kind of misspoke before. But if you integrate the rate at which position changes, you'll actually get the change in position. It's really important topic. Integrate the rate next year. Integrating rates of change, which I believe you do in AP Chem anyway. Way before we get to it, way before you even get to AP Calculus, if you're taking it in 11th grade. It's something cool to talk about, though. It's the accumulated change. You don't need to worry about any of that. You don't need to worry about the expansion and getting your answer. But, you know, maybe it piqued a couple people's interest right there. Let's move on to number 4. Number 3 is for homework, which is good because it got cut off kind of when I tried to print it. Number 4 over here, cool problem, okay? And there's a lot going on in this problem right here. And it's really like the last new problem we're going to do for the entire year. So I promised myself I wouldn't cry, and I won't. Even though I do really miss some people. Some people, not so much. Mostly teachers like Mr. Pushy. The rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. A lot of stuff going on there, you know. And then they tell you the graph of r and a selected table of values for r of t from 0 to 90 are shown above. So here they actually give you a function represented graphically and numerically. It's very rare, okay? Normally we just get, you know, one of those things, and sometimes we get functions given algebraically as well. They want to give functions orally now. They want to say it's the 4th thing. Used to be the rule of 3, algebraically, graphically, numerically. Rule of 3, where my Star Wars fans, rule of 2, little Sith action. Now they want to say the rule of 4 because they want to say orally, but it's kind of hard unless I hit something and it says play to give you information about a function orally. But one of these days, you'll probably be taking the AP with like headphones on and stuff like that. So the rate of fuel consumption, one more time, in gallons per minute recorded during an airplane flight. Pretty important, right? To know how much fuel the plane is consuming. Okay, you wanted to analyze that information, okay? So you can make sure planes have enough fuel to get where they're going. You don't want to have too much excess fuel as well, because you don't want to be spending extra money on fuel. All these things go into, when you're dealing with companies and such. There's math behind really everything. Strictly increasing, that's important, because just this info over here wasn't enough to say it's strictly increasing. Who's to say between 0 and 30, it didn't, at 0 to 15, it didn't go down to negative 50. And then all of a sudden from 15 to 30, go from negative 50 to 30. We don't know. People assume. You know what happens when you assume? It's inappropriate. I can't say it on an instructional video, but you know. But they tell you it's strictly increasing. And they also give you the graph, which tells you a lot of information. Check this out. Approximate the value of this integral right here. No big deal, right? It's just approximating a definite integral. Now it says using a left Riemann sum. No big deal right there. But now it says with the 5 subintervals indicated by the data in the table. Then they actually want to know if the approximation is less than or greater than this guy right here, which is cool. Upper sum, lower sum. We spoke about that a little bit. The subintervals of equal length is the important thing, because if you want to set up your normal expansion, you'll do this, right? I'll write it over here so it's wrong. You don't have to write this down. We'll say, oh, you got to start with delta t, right? Which is b minus a over n. So in this case, the bounds are 0 and 90. So 90 minus 0 divided by 5, right? 5 subintervals of equal length. So 5 into 90. I don't know, can you see what I'm writing? What's 5 into 90? What's 5 into 40? 5 times 8. Okay, so that's 18. Okay, so delta t would actually be 18 in this case. You start by putting your 18. And then you have your first f of, but it's not an f of this time. It's an r of, right? And you think of the first rectangle, like, yeah, that first rectangle is going to start at the lower bound, which was 0. It's going to end at 18. And what they want? A left Riemann sum. So plug in the 0. And then we just keep adding delta x's, right? Plus r of 18. Plus r of, add another 18, gives us what, 36. Plus, and you keep going here, but there are problems. See, r of 0 is okay, because I know what r of 0 is equal to, but I don't know what r of 18 is. It's not in the table, and here you could try to approximate it, but you don't know exactly what it is. This is not gonna work, okay? Sometimes you're restricted with the information you have. It's not 4 subintervals of equal length, so you can't factor out that delta t, okay? Here, what we're gonna need to do is we're going to need to actually get the area of each rectangle separately, okay? Which is how we started doing this on the last video. Now the integral from 0 to 90 of r of t with respect to t is approximately, you know, it's a different delta t for each of these subintervals. You know, what subintervals indicated by the data in the table? Well, the first one's from 0 to 30. That's your first subinterval. That's a delta t of 30, right? The base would be 30. The second one's from 30 to 40. That's a delta t of only 10. And then from 40 to 50, the third rectangle, once again, a delta t of only 10. Then a delta t for the fourth rectangle of 20, and then another delta t of 20 right there. So the reason this is such a good problem to start with these types of problems with, and it's only one we'll do this year, we'll do more next year, is the graph is cool because you can see the first one, we go from 0 to 30. So that's our first rectangle right there, rectangle 1. And then we're going to go from 30 to 40, 40 to 50, 50 to 70, Mr. Harrington's age. And then from 70 to 90, I was lying, that's really Mr. Harrington's age. Rectangle 2, 3, 4, 5. And now look, you can see that each of them, different delta t's. They have different bases. And the heights are, it's a left Riemann sum. So the first one, you're going to plug in the 0 to determine the height, not the 30. Plug in the 0. Here's our height. Draw a horizontal line. Wow, that's terrible, Berto. Somewhere I can hear Hannah Kleinman laughing at me. She always does when I mess things up on the board. Thanks a lot, Hannah. Anyway, so now from 30 to 40, rectangle 2, it's a left Riemann sum. We'll plug in the 30 to determine the height. So that's what my second rectangle would look like. Then we'll plug in the 40 to determine the height. Rectangle 3. Rectangle 4, we'll plug in the 50 to determine the height. And finally, for rectangle 5, we'll plug in that 70 to determine the height right there. And you can see it's an under approximation, which is going to be important later. But really, you just got to get each area separately. And some people might do this. They might be like, all right, the area of the first rectangle, they'll just say it's 30 times 20. I'm going to say 30 times r of 0. Same thing as 30 times 20, but they want to see that. They want to see the expansion with the function in there, okay? Plus, you know, that the second rectangle, I know, has a base of 10 times his height, which is r of 30, right? Because I want to plug in that leftmost x value. Okay, plus the third rectangle has a base of 10 as well. You can even do it. You don't need the graph, right? Over here, you look at the third rectangle. You're like, oh, it's a left Riemann sum, so I'm going to plug in the 40, the lower value right there. Plus, now I know the fourth rectangle has a base of 20. And I know I want to plug in the 50. Excuse me, yeah, the fourth rectangle, so the 50 right there. So you can see the 50 is going to be the leftmost value, so r of 50. Okay, plus finally 20 times r of 70. Okay, and just like before, left Riemann sum, we'll start with r of, in this case, the lower bound, and it'll end with r of, in this case, this delta x of 20 to the left of the upper bound right there. And, you know, and then you can go into saying, okay, this is really 30 times 20 plus 10 times, what was r of 30? 30 plus 10 times, what was r of 40? 40, hopefully not your test grade, 40, plus 20 times r of 50, which is 55, speed limits in certain places, plus 20 times r of 70, which you know is 65. Speed limits in other places. Let's do it without a calculator. You think I'm going to screw it up? Let's see. 30 times 200, 30 times 20. I don't even know what the numbers are. I could do that. 600 plus 3 hundo, fishundo, plus 4 hundo, fishundo. 20 times 55. You know, 2 times 55 is 110. You add a 0 to it. 110, road that's perpendicular to Jericho Turnpike. 20 times 65. 65 times 2 is 130. Put a 0 on it. And add these up, I don't know, in a useful way. Is there an easy way to do this? Check this out. 300 plus 400 is 700. 700 plus 1300 is 2000. 2000 plus 1100 is 3100. Plus 600, 3700. That's our answer right there. Is it less than the value or greater than the value? We know it's less than the value. It's an under approximation. You can see from the way we squared it off. We're going to say under approximation. I don't know if you could even read that. That says under approximation. That's really all you need right now. You know, next year on the AP, you'll have to justify it. And it's because r of t is increasing. So let's write that down just for the heck of it. You'll see with left sums and right sums, you'll be able to know if they're upper sums or lower sums, under approximations or over approximations, without even thinking about the graph. Just, you know, thinking about whether or not the function is increasing or decreasing. Usually information that they'll give you. And then as far as units, if you integrate gallons per minute, that's the rate at which fuel is being consumed. If you integrate the rate at which fuel is being consumed, you're going to get the change in the amount of fuel that was consumed from t equals 0 to t equals 90 minutes. So you're really going to get the amount of fuel that was consumed over that 90-minute flight. Okay, and fuel would be in gallons here. So technically, gallons is going to be my unit right there. We'll talk more about that next year, but if you integrate the rate at which a quantity changes, you get the change in that quantity. That's our last instructional video for this year. Okay, remember, having Google Meets 8:30 Monday morning. If you have a question on anything, and look, went through a lot of stuff with this distance learning, and I can't tell you how much I really do, as much as I joke about it, miss having you guys in my classroom. And just thanks for a great year, a great group of kids, you know, with some exceptions. No, just kidding. Really, all of you, fantastic students. I'm really looking forward to some great things, you know, in calculus next year. Remember, don't just take BC calculus on a whim and just be like, well, my friend's taking it, so I'll take it. You better be ready to work in that class, okay? AB calculus, same thing. It's not an easy class, okay? BC is going to be much quicker. Going to play around with some different stuff and things like that. So look, just make sure you put yourself in the appropriate spot. I know scheduling is difficult as well, but if you're like, well, I want to take AB, but my schedule only, you know, sets it up so I could take BC, so I'll try BC out. That could be very tough, okay? There's definitely some people who are not cut out for the BC curriculum. It's not an insult to you or anything like that, okay? So look, you want to have a conversation with me about it? Send me a reminder, send me an email, we'll talk about it, okay? And don't worry, we'll figure out what's best for you. Don't think you need to take advanced placement calculus. No, some people are like, well, you know, I have to take it. Everybody's taking all these AP. You don't, okay? You know, I use Mr. Pushy as an example, as much as I hate him. You know, he's really my friend, right? He was in my wedding party. You know, I'm sure you think he's an excellent teacher. God, it hurts me so much to say that. Really. But he is, right? He's a good teacher. No, I can actually say that because I trained him. He's my protege, you know, so, you know, he learned everything from me. No, he's a great teacher, and he didn't take advanced placement calculus in 12th grade. Well, he teaches AP Stat. Will you stop? Okay, you know, look, just telling you, you don't need to take 5,000 AP courses. But if you want to challenge yourself, great, okay? Just be ready to put in work. Like, if you want to take AP Calculus next year and you've been slacking off not doing videos, what are you doing? Unless you're one of those kids who can sit there and just understand everything instantaneously, which is very difficult. I know you exist, but it's not as many of you as you think it is. And also in BC, you might meet your match, or you might not. You might still be bored. Search your feelings. You know it to be true. I don't know. I don't even know what I'm ranting about right now. I just want to say that you're a great group of kids, okay? And you're all going to be able to attain all of your dreams, okay, as long as you put in the work. Don't worry about missing out stuff this year. I know you're probably upset about that, but you're going to be okay. In the long run, you really are. And if you watch my videos, you really didn't miss anything in here at all, unless you want to just, you know, watch me jump up and down in class and start breathing heavily. Anyway, so that's it. Next year, like I said, final review. If you have any questions, get in touch with me, and stay safe and healthy. Adios.